Hi guys, welcome back. So today we are going to be working with complex numbers. Round one or round now, we are going to be taking complex numbers, simplifying them, and then for added spice, we will add them, subtract them, and multiply them. Now, you may ask yourself, what about division? Are we not going to do that? Because if we're going to do 3 out of the 4 basic operations, we might as well do the fourth one. We are going to do the division, but we're going to hold that for round 2. So I guess you have to be back, okay? I should be a writer. All right, let's do this. Now, we're going to open up this unit with the imaginary unit. I'm just going to copy what I wrote down. What is the imaginary unit? Okay, so the imaginary unit is noted by the lowercase I. What does it represent? The imaginary unit I is pretty much the principal root of -1. In English, I, or the imaginary unit, equals square root of -1. As a result, if we were to square both sides, when we square the left, that will give us I squared, and when we square the right, that will give us -1. Why? Because the square and the square root will undo each other. Now, the question is, how do we simplify square roots of negative numbers? Okay, if you have the square root of a negative number, let me go ahead and copy this. Okay, if you have a square root of a negative number, the first thing you need to do is make the radicand positive. So in this case, we are going to replace the square root of -1. Let me write it a little bit differently. Okay, so we're going to write it as -1 times b. Okay, so if you have a negative radicand, the first thing we want to do is make the radicand positive. How? We're going to replace the square root of -1 with what? Yeah, that's right. We're going to replace the square root of -1 with the imaginary unit I. Then once our radicand is positive, then do what you got to do to simplify it. Okay, so let's go ahead and knock out a fun problem number 1. It says simplify. You may not use a calculator to answer. Okay, so let's do this. Square root of -4. Who knows what that is? I don't. Okay, the first thing we want to do is fix it so the radicand is positive. How? We're going to replace the square root of -1 with the imaginary unit, or just say replace it with I. So we have square root of -1. We're going to swap that out for I, or the imaginary unit, and that will leave us with the square root of 4. Sorry, like this circle was like a little too big. Now that the radicand is positive, we're going to do what we have to do to simplify it. Okay, square root of 4, if I can read your mind, I believe is 2. And that's pretty much the answer, I2, or I times 2. But although it's not a variable, it's not aesthetically pleasing to put it before the 2. So it is preferred if you put it after. Cool, fantastic. 1 problem down, 2 more to go. So now problem B, we have negative square root of 49, or opposite of the square root of -49. The worst thing you can do to yourself, let me go ahead and write this over. Okay, so this is wrong. So let me just put wrong. Don't do this. Okay, sometimes I don't like to put the word wrong, but I'm hoping that if I write it, it will highlight. Students will sometimes say, oh look, product of 2 negative numbers is a positive number, so that will give us square root of 49, and then that will give us 7. So again, this is incorrect. So the radical sign is not a parenthesis where you can just distribute. Okay, you got to take care of the inside first before you look at the outside. So let's go ahead and do this correctly. So first we're going to focus our energy on simplifying the square root, and then we'll bring down the rest of the problem. Square root of -49, who knows what that is? I have no idea. So again, to simplify the square root of a negative number, the first thing you need to do is fix it so the radicand is positive. So we're going to replace the square root of -1 with the imaginary unit I. Okay, so we have I times the square root of 49, and then we're going to bring down the rest of the problem. Okay, fantastic. So now we keep our cool and simplify what we can. So we have -I times the square root of 49. I believe that gives us 7. That's the answer. We can't simplify it further, but we want to write this so it's aesthetically pleasing. So I would appreciate if you just put -7, then the times I. Fantastic. 2 problems down, 1 more to go. Problem C. So we have square root of -8. So what is the square root of -8? Who knows? Okay, we know it's not a real number. Okay, because square roots of negative numbers represent non-real numbers. but we are asked to simplify it, not just to classify it. So first things first, we need to fix it so the radicand is positive. So what are we going to do? We're going to replace the square root of -1 with the imaginary unit I. So I keep saying replace the square root of -1, although we don't explicitly see the -1. So I got a little bit excited, but if you like, you can just rewrite -8 as -1 times 8, and then we can explicitly see, oh yeah, I get you, Miss Torres, you know. The first thing we need to do is make the radicand positive. So how are we going to do that? We're going to replace the square root of -1 with the imaginary unit I. Okay, so do what you got to do. Okay, so let's come back to our problem. Okay, so problem C, we need to make the radicand positive. How? We're going to replace the square root of -1 with the imaginary unit I. And then that will leave us with I times the square root of whatever we're left with. 8, unlike 4 and 49, is not a perfect square, so we got to think of a perfect square factor. I believe it's 4. Okay, so a nice way to rewrite 8 will give us 4 times 2. Pretend I said square root of 4 times the square root of 2. Okay, do what you got to do. The square root of 4 simplifies to 2. The square root of 2 will stay as square root of 2. And although we cannot simplify this further, we need to write our answers aesthetically pleasing. So we're going to first put the factor of 2, then the I, then the square root of 2. So 2i square root of 2. Now, someone said, I read ahead, and then the book says something about a plus bi, whatever that is. Shouldn't we write our answer as 2 square root of 2 times I? Okay, technically we should, but the reason why when we have a radical left, the reason why we're given the green light to put the I before the radical is just to make sure that we don't accidentally put the I inside the radical. So this is not recommended. Cool. Alright, so we are getting close to our first addition problem, or multiplication and subtraction. But before we can do that, let's talk about complex numbers and standard form. Okay, we had just said, oh, we're gonna add, subtract, and multiply them, but we never actually formally defined what is a complex number. Okay, so a complex number is pretty much a number that can be written in this form: a plus bi. Okay, a complex number is a number that can be written in this form: a plus bi. So you can read, but I will point. So in this case, a represents the real part, and then bi represents the imaginary part. Okay, depending on the book will say that B represents the imaginary part. Okay, I want to point out that I is the imaginary unit that we have from above. So I represents the square root of -1, and A and B represent real numbers. Okay, now when you have a non-real answer, if you have more than one term, so right here we got a non-real answer, one term, one term, one term. When you have a non-real answer and you have more than one term, we need to write our answer in standard form for a non-real number, which is, you guessed it, a plus bi. Okay, so in short, I want you to put the real part first and then the pure imaginary part at the end. If you only have one term, then you don't have to worry about which one goes first. Okay, so let's go ahead, look at complex numbers. So it says names of complex numbers. So we have imaginary number, pure imaginary number, real number. All of these are complex numbers. Okay, but we break it down. Okay, so when I hear the word complex number, this is what I think: something like 3 plus 5i, something that has an I. Okay, cool. So why is this an imaginary number? Why is this imaginary number a complex number? A complex number is a number that can be written in the form a plus bi, where a is the real part and bi is the pure imaginary part. I'm going to jump straight to a real number. Okay, why are real numbers complex numbers? So let me toss in my favorite number, 3. It's a lie, it's not my favorite number, but I just put it just so they look the same. Why is 3 a complex number? I thought 3 is a real number. 3 is a real number, but why is it also a complex number? Well, 3 is a complex number because it can also be written in the form a plus bi. In this case, we can write it as 3 plus 0i. Okay, cool. Pure imaginary number. Okay, what does that mean? So pretty much it's a complex number that only has the sorry for the redundancy, the pure imaginary part. So in this case 5i. Okay, so why is this pure imaginary number a complex number? Well, we can also write it in the form a plus bi. In this case, the real part is 0. Okay, I think I overanalyzed this for some weird reason, but it's okay. My intentions were good. So let's go ahead and get down to the nitty gritty. We're going to do a set of 7 problems and then we're out. Give me a sec. Alright guys, so those 7 problems have been found. Lucky you. Okay, so a quick reminder, when we had talked about the product and quotient rule for radicals, the product and quotient rule for radicals hold true only when the radicand is positive. Okay, so if you have the square root of a product, we can split the factors. We can write it as, let me just go ahead and write it. Okay, if we have the square root of a product, we can just split the factors. We can write it as square root of the first factor times square root of the second factor. But again, the product rule for radicals only holds true if our radicand is positive. The quotient rule for radicals, I'm just copying it, okay? The quotient rule for radicals says, or for square roots, I should say, okay, because it's explicitly for square roots. The quotient rule for square roots says this: if you are square rooting a fraction, you can also split it. How? You can write it as square root of the numerator over square root of the denominator. But again, I want to highlight that these properties hold true only when the radicands are positive. So in English, only when you're square rooting positive numbers. So fun problem number 2. Let's do these 7 problems and we're out. So the directions read add, subtract, multiply, or divide as indicated. So if you see a plus sign, then you add. Same thing for the remaining 3 operations. Now, we're going to be working with complex numbers or non-real numbers, however you want to dish it out, okay? When it comes to working with complex numbers, it's implied that you write your answer in standard form, okay? Because this is day 1, then I will make sure to always put, hey, write your answer in standard form. Standard form for a complex number is a plus bi, real part followed by pure imaginary part. So we have problem A. We have square root of negative 16 times the square root of negative 36. The first thing we need to do is fix it so the radicands are positive. So we're going to replace the square root of negative 1 with the imaginary unit I. Okay, and then that will leave us with I times square root of 16. We're going to multiply that by square root of negative 36. The first thing we need to do is fix it so the radicand is positive. So we're going to replace the square root of negative 1 with the imaginary unit I. If you need to remind yourself, go for it. Remind yourself as many times as needed. And that will leave us with I times the square root of whatever we're left with. Okay, so I times the square root of 36. Fantastic. So now that our radicands are positive, you're going to do what you're going to do. Let's go ahead and simplify the square roots and then take it from there. Last time I checked, square root of 16 is 4. Last time I checked, square root of 36 is 6. Fantastic. So now for the grand finale, I want to know what's the product of I, 4, I, and 6. With your permission, we're going to multiply the integer factors first, and then we'll multiply the i's at the end. Okay. Product of 4 and 6 will give us 24. Product of I and itself, we use exponents or repeated factors, and that will give us I squared. Or you can say silly exponent rules. They make me so mad. Okay. Now, if in your answer you have a reference to I, the only I that I want to see is I to the first power. I raised to any power other than 1 can be simplified. Should you memorize what I squared is? I mean, you can if you want, but I've said it before. Memorize what you have to and digest as much as you can. You can only memorize so much, okay? So if you're like, oh, I'm going to memorize these 2, you can, but it would be such a shame. Just memorize the meaning of the imaginary unit I and then take it from there. So I'm going to bust out a thinking area. So I was like, oh man, I want to know what I squared simplifies. I know that I equals square root of negative 1. How can I build the I squared? So I'm going to use my bad notation, but it is what it is. So we're going to take that I and square it. Okay, so we're going to square both sides, and when we do, the square of I is just square of I, and then on the right side the square and the square root undo each other, and that will leave us with -1. Okay, so pretty much just build it. Okay, and if you build it, you don't have to I feel like that movie, what does they say, if you build it they will come. Yeah, okay, cool. So again, I wouldn't recommend memorizing another fact. Just remember one and then build it to get what you need. So let's go ahead, simplify this. So I squared, thanks to our hard work, simplifies to -1, and the product of 24 and -1 gives us -24. Fantastic. Okay, so remember, we're doing 7 problems. This is our first problem. Problem B, we have, where am I? Square root of -50 times square root of 6. Okay, so square root of -50 times the square root of 6. Now, if both radicands were positive, then we have the option to multiply the radicands now and then simplify later. But in this case, because both radicands are not positive, then we cannot use the product rule for square roots. Okay, so first things first, if you're working with square roots of negative numbers, your primary goal is to fix it so the radicand is positive. So we're going to replace the square root of -1 with the imaginary unit I. Okay, so we have square root of -1 swapped out for I, and that will leave us with I times the square root of whatever we're left with, namely 50, and that is being multiplied by the square root of 6. Okay, now that the radicands are positive, you have some options. You can simplify each square root now and then multiply later, or you can multiply the radicands now and simplify later. My recommendation is to always simplify first and then multiply later. Why? Because I would rather work with 50 and 6 versus the product of 50 and 6, which I think is 300. Okay, so a perfect square factor of 50, I think is 25, because if I have 50 cents, I have some quarters. Okay, I want to listen to rap music now. Okay, so we're going to rewrite square root of 50 as the square root of 25 times the square root of 2 and simplify whatever you can. Square root of 25, last time I checked, gives us 5, and that will leave us with the square root of 2 times the square root of 6. Fantastic. Okay, so do what we got to do. Let's make this look pretty or aesthetically pleasing. Product of I and 5 is the same as product of 5 and I, and we're going to go ahead and multiply the radicals. So let's use the product rule for square roots in reverse. Product of 2 and 6 will give us 12, and at this point I'm pumped because I'm like, we got it. You know, we got 5 I times the square root of 12. Our radicand is positive, so we're good. But check it out, when it comes to radicals, you need to make sure that it's simplified all the way. And in this case, square root of 12 is not simplified because it has a perfect square factor, namely 4. So let's go ahead and do this. We're going to rewrite the square root of 12 as the square root of 4 times the square root of 3, and then do what we got to do. Last time I checked, the square root of 4 simplifies to 2, and that is being multiplied by the square root of 3. So let's go ahead, clean this up, multiply outside factors with other outside factors, and then I was going to say the radicals with other radicals, but they have been dealt with. Product of 5i and 2 will give us 10i, and that will leave and that will be multiplied by the square root of 3. Now someone said, oh, Miss Torres, what about standard form? The only time you really have to worry about standard form is if you have more than one term in your answer. But in this case, once again, we only have one term in our answer, so we don't have to worry about writing our answer in a standard form for a complex number. Alright, so that's number 2, which means I think I owe you how many more? 3. I don't know. I don't know how to count. Oh my gosh, I should get a new job. Alright, problem C. Problem C, we have square root of -40 over square root of 10. Okay, this problem is such a teaser. Why? Because I really want to cancel out 40 and 10 by a factor of 10, but we can't do that for 2 reasons. One, because they're not housed under the same radical, and 2, the quotient rule for square roots only holds true if the radicands are positive, and in this case they're not. So first things first, we need to make this radicand positive. How? We're going to replace the square root of -1 with the imaginary unit I. So let's do this. So that will leave us with I times square root of whatever we're left with, 40, over square root of 10. cool. I'm not a big fan of writing across, but when there's no space, there's no space. Okay, I'm gonna go ahead and use arrows because one of my pet peeves is when I see equal signs written across. Equations only have one equal sign. So let's go ahead and use the quotient rule in reverse to house 40 and 10 under the same radical or the same square root. Okay, yeah, remind me not to use that color again. So we're going to write this as I times the square root of that quotient, square root of 40 and 10. Okay, so let's keep our cool. Quotient of 40 and 10, or in English, 40 divided by 10 will give us 4. And last time I checked, the square root of 4 is 2. And that is the answer. We cannot simplify it. We just want to make it look pretty or aesthetically pleasing. So we'll put the integer factor first and then the imaginary unit at the end. Okay, fantastic. Okay, so that's number 3. If I know how to count to 7, we need 4 more. Give me a sec. Alright, so number 4 has been identified. So we have square root of negative 72 times the square root of negative 8. Okay, first things first is we need to make sure that the radicands are positive, and then we do what we gotta do. Okay, so we are gonna replace the square root of negative 1 with, you guessed it, the imaginary unit I. So that will leave us with I times the square root of 72 over, same speech, let's replace the square root of negative 1 with the imaginary unit I. So that will leave us I times the square root of 8. At this point, it's a work our magic and then cancel out whatever we can, namely the factors of I. Now, if at this point, if you want to cancel out 72 and 8 by a factor of 8, go for it. I never recommend that because sometimes when you start to cancel things out and they're not under the same radical, then you want to cancel out things when you're not supposed to, like when one factor is inside and another factor is out. So let's go ahead and use the quotient rule for square roots to write it under the same roof. So that will leave us with square root of 72 divided by 8. Last time I checked, who has a calculator? 72 divided by 8 will give us 9. And then with confidence, the square root of 9 will give us 3. Now, someone asked, what happened to standard form a plus bi? The only time we have to worry about writing our answer in standard form for a complex number is when you have more than one term. We have done 4 problems, but like all those 4 problems only have single terms in their answers, so we don't have to worry about standard form. Hopefully we'll have to worry about that in a bit. Okay, I want to give you all these case scenarios. Problem E, let me go ahead and write it. We're going to put an open parenthesis, negative 3 plus 2i, close parenthesis, plus, where am I, open parenthesis, 1 minus 3i, close parenthesis, plus open parenthesis, negative 7 minus 5i, close parenthesis. So pretty much we have 3 complex numbers. All of them are separated by a plus sign, so we are asked to add these complex numbers. Someone asked, well, how do we add complex numbers? I love adding complex numbers. You just got to think about combining like terms. We're going to add all the real parts together, and then we'll add all the pure imaginary parts together. Now, I know you're very gifted and you can easily go straight to answer. Maybe I can too, but you'd be surprised how many times I make careless mistakes because I try to do everything in my head. There's something about me writing it on paper that kind of helps me not to make that mistake. So let's go ahead and do this. We're going to rewrite this without those parentheses, okay? So like this first complex number, there's nothing to distribute. The parentheses are there just to let you know that these two go together. That's our first complex number, that's our second complex number, and that's our third complex number, okay? So we have negative 3 plus 2i, and then we're going to add to it the second complex number. Again, there's nothing to distribute, so let's bring down the terms as is, and then we're going to add to it our third complex number, which is negative 7. I'm going to wrap this up because this plus negative action doesn't really work for me, minus 5i. So at this point, you can just be like, okay, cool, the sum of the real parts is this, the sum of the pure imaginary parts is this. But this is a little bit hard on my eyes, so with your permission, I'm going to love myself like I always do, and then I'm just going to write the like terms side by side. So I'm going to first write all the real parts, and then I'll write all the pure imaginary parts. So we have negative 3 plus 1 plus -7, we'll just go straight to -7. Okay, so I'm going to put all the real parts first, followed by the pure imaginary parts at the end. So we have 2i minus 3i minus 5i. So someone said, do we really have to rewrite it like this? No. Can we just go straight to answer for this problem? Yeah. Okay, but let's do this. -3 plus 1 is -2. Oh, how come I don't subtract 7 from it right now? Because I said it before, when I do more than 2 things at a time, I make silly mistakes. Okay, so just be careful. Difference of 2i and 3i will give us -i. We'll bring down the rest of the problem. Okay, I love myself, so I'm not afraid to take that extra step. If taking the extra step is what I need for me to make sure that, for me to minimize the likelihood of a careless mistake, so be it. Okay, so let's clean it up. Difference of -2 and 7 will give us -9, and then difference, or I should say sum of -i and -5i will give us -6i. Okay, -9 and 6i are not like terms. -9 is a real number, and then 6i is a pure imaginary number. Now, someone asked, is it okay if we put -6i minus 9? Okay, the expressions are equivalent. Okay, 9 is still negative and 6i is still negative. Now the question that you want to ask me is it will we get full credit for it? And the answer is no. Okay, why not? The reason why we wouldn't get full credit is because we are asked to write our answer in standard form. Standard form for a complex number is a plus bi. So I need to see the real part followed by the pure imaginary part. In English, put the I part at the end. Okay, so this is what we need to see. Okay, so that is problem E. Let's go ahead do problem F. Okay, so problem F, we have open parenthesis -10 plus 6i close parenthesis, and we're going to subtract from it open parenthesis -10 plus 11i. So the parentheses are pretty much there to let you know that these two go together, so that's our first complex number, and these two go together, so that's our second complex number. So we have two complex numbers separated by a subtraction sign. The question is, how do we subtract complex numbers? Well, it's going to be the same speech. We're going to subtract the real part, and then we're going to subtract the pure imaginary parts. For me, it's very difficult to go straight to answer because, again, if I don't write it out, I'm going to make a silly mistake. Okay, so let's do this. For the first complex numbers, the parentheses are not needed. There's nothing to distribute, so let's drop them like they're hot. Yeah, all right. So 10 is negative, so we have -10 plus 6i. And then we're going to apply the rule for subtraction. You know, so someone said in pre-algebra, subtraction sucks. Let's go ahead and add the opposite. Don't tell my boss I said that, okay? Okay, so I'm going to just say it a little bit differently. Okay, guys, rule for subtraction is what? Addition of the opposite. Okay, if you don't like that, then just say distribute the negative. Same difference, okay? So when we add the opposite of a negative term is a positive term. Opposite of a positive term is a negative term. Okay, so the first thing we need to do is to write the subtraction problem as a related addition problem and then take it from there. Okay, we only have 4 parts, so I think I'm gonna be like an overachiever and go straight to answer. The sum of the real parts, namely -10 and +10, will give us 0. And the sum of the pure imaginary parts, namely 6i and -11i, will give us -5i. In our answer, we only have one term, so we don't have the real part and the pure imaginary part, so we don't have to worry about, oh, don't forget to write the answer in standard form. Okay, guys, so we simplified some radicals that had negative radicands. We had an addition problem for complex numbers. We just knocked out a subtraction problem for complex numbers. The one that I owe you is a multiplication problem. So let's go ahead and do lucky number 7 and then we're out. Cool. Problem G. We have our first complex number, 5 minus 4i. And then we're going to multiply it by this second complex number, which is 2 plus 7i. Okay. So the question is, how do we multiply complex numbers? To multiply complex numbers, you're going to multiply like if they were polynomials, or to be more specific, like they were binomials. Like if we had a binomial, we would just say FOIL it out, and it's no different here. So let's go ahead, FOIL it out, take care of our four products, combine what we can, and then we're good. Okay, product of the first terms, namely 5 and 2, will give us 10. Product of the outer terms, 5 and 7i, will give us 35i. Product of the inner terms, negative 4i times 2 will give us negative 8i. And then product of the last terms, negative 4i times 7i will give us negative 28i squared. Fantastic. So we got a lot of terms. Let's combine them and then make sure that our answer is in standard form. Standard form for a non-real complex number. Okay, so we have one real term. The sum of the middle terms. Who has a calculator? 35 minus 8i, 27. Yeah, I use my fingers, okay? Plus 27i minus 28i squared. Okay, so if we are gonna have a reference to I need to see a flat I. Okay, I, not I squared, not I cubed, not I to the fourth, just I. So you have options. You can either memorize what I squared simplifies to, which I highly do not recommend. Okay, I would recommend that you build it up. Okay, so the only one that I'm gonna remember is the meaning of the imaginary unit. Okay, I, or the imaginary unit, represents the square root of negative 1. But I want to fix it so it looks like I squared. So let's go ahead, square both sides. Y squared, because we want to know what I squared is. When we square both sides, the square of I is just the square of I, or in English, I squared. And on the right side, the square and the square root undo each other, and that will leave us with negative 1. Okay, so we can very quickly build it. Okay, so that will leave us with negative 28 times I squared, and I squared simplified to negative 1. Let's continue to work our magic and simplify whatever we can. Product of negative 28 and negative 1 will give us positive 28. We got three terms. We can combine them, and remember, when we have complex numbers, we need to put them in standard form. Okay, a plus bi, real part followed by pure imaginary part. The sum of 10 and 28 is 38, and then we're going to add to it the pure imaginary part, which is 27i. Okay guys, so I said we were going to do 7 problems. That was our 7th and final problem, so we're out. Thanks.